Welcome to Thought Frontier.
All right, so you stumble across a dusty old time machine, right? Hidden away in your attic. Where would you go? Ancient Rome. Witness the first human colony on Mars.
Tempting.
I know, right? But maybe you'd be more tempted to rewrite some of those, well, less than stellar moments from your past.
Yeah, we've all been there.
But here's the thing. What if? What if time travel wasn't just something from the movies? What if it was actually, potentially, maybe possible?
Now that's a question worth exploring.
And that's exactly what we're doing today. We're diving deep, deep into theoretical physics to find out if turning back the clock might actually be in our future.
It's a fascinating question, no doubt. And the really exciting thing is we're not just dealing with speculation here. There's actual science to grapple with. We've got a whole stack of sources for you today. An encyclopedia entry on something called closed timelike curves.
Okay, those sound intense.
They are. Plus, we've got some intriguing academic papers, a new scientist article, and even a YouTube video that dives into the work of physicist David Deutsch.
David Deutsch, the fabric of reality guy.
The one and only. His ideas on quantum time travel are mind-blowing.
Okay, so we're talking Einstein, quantum mechanics, paradoxes, the whole shebang. Sounds like my kind of deep dive. But before we get lost in the quantum weeds, can we break this down a little? Is time travel actually a thing, or are we just, messing with our brains here?
Well, the crux of it is the very laws of physics, specifically Einstein's theory of general relativity, might actually allow for the theoretical possibility of time travel.
Wait, so Einstein's theory is on board with the whole time travel thing? That's pretty wild. Tell me more.
So Einstein's theory of general relativity, it describes how gravity warps both space and time. And within that framework, there's this concept called closed timelike curves, or CTCs for short.
CTCs, got it. What are those exactly?
Imagine, if you will, a coffee cup.
Okay, coffee cup. I'm visualizing.
Time is flowing upwards, space is the circular rim, and that handle, that's a CTC, a path that loops back to the past.
So it's like a cosmic shortcut through time. That's incredible. But hold on. If Einstein's theory allows for these CTCs, these time loops, wouldn't that mean, shouldn't we be running into time travelers all the time?
Right. You'd think so, wouldn't you?
I haven't seen anyone sporting a powdered wig at the coffee shop lately.
No, me neither. And that brings us to one of the biggest head scratchers when it comes to time travel.
Paradoxes.
Paradoxes, right. Okay, like what? Give me an example.
Well, the most famous one is the grandfather paradox. Imagine you build a time machine, go back in time, and, you accidentally bump into your grandfather. He misses his date with your grandmother, and poof.
Poof, what?
Poof, no parents, no you, no time traveler. It just creates this impossible situation.
Right, like a cosmic glitch in the system.
Exactly. And physicists have been grappling with these kinds of paradoxes for decades.
Okay, yeah. I see how messing with the past could get really messy really fast. But I thought we were talking about quantum time travel. Does quantum physics have a solution for these paradoxes? Some kind of, workaround? Now that's where things get really, really interesting. See, quantum mechanics, which governs the world of tiny particles, has a very different take on time compared to general relativity.
Oh, really? How so? Are we talking parallel universes, alternate timelines? That kind of stuff.
Not quite, although those ideas are fascinating in their own right. In quantum mechanics, time is more like a rigid backdrop, unchanging, straightforward.
Okay, so rigid versus flexible then.
Exactly. And this creates tension. You've got rigid quantum time clashing with general relativity's flexible space-time, where time can be warped and bent. And this tension, well, this is where things start to get exciting.
A clash of the titans. So Einstein's bendy spacetime on one side and quantum mechanics' rigid time on the other. How do we even begin to reconcile these two?
That is the million-dollar question. And one potential bridge between these seemingly contradictory theories is a concept called retrocausality.
Retrocausality. That sounds like something straight out of a sci-fi movie.
It might sound like science fiction, but it's an actual idea in quantum physics. Imagine two entangled particles, right?
Okay, entangled.
They're linked in a way that measuring one instantly affects the other, no matter how far apart they are.
Yeah, that's spooky action at a distance, right?
Precisely. Retrocausality suggests that this entanglement might actually be the particles communicating backwards through time.
Hold on. Wait. You're saying that by measuring a particle now, we could be influencing its entangled partner in the past? Like sending a message back in time?
You got it. It challenges our whole understanding of cause and effect. It's like the result of an action is influencing the action itself.
Okay. My brain needs a minute to process this. So we've got these particles potentially talking to each other through time, and somehow that could resolve the time travel paradoxes.
It's a possibility.
But how? How can you change something that's already happened?
Well, there are two main models of quantum time travel that attempt to answer that very question.
Two models. Okay, lay them on me.
The first one is called Deutschian CTCs, named after, you guessed it, David Deutsch.
Okay, Deutschian CTCs. Let me guess, in this model, I can go back and finally fix that embarrassing karaoke performance from college.
Not so fast.
Uh-huh.
Deutschian CTCs are all about self-consistency. They say that whatever you do in the past, it has to lead to the present you came from. It's like a closed loop. Any changes you make have to ultimately bring you back to your starting point.
So no rewriting history. No do-overs.
Afraid not. At least not in this model.
No stopping myself from belting out Bohemian Rhapsody completely off-key. Bummer.
Okay, but you said there were two models, right? What's the other one?
Now the second one is even wilder. It's called post-selected CTCs.
Yeah.
And for this one, imagine that reality is constantly running through all possible outcomes, like a giant quantum computer exploring every potential scenario.
Reality as a giant quantum computer. Okay, got it. I'm with you so far. But where do these post-selected CTCs fit into all of this? So with post-selected CTCs, we only see the outcomes that fit a specific set of criteria. It's like reality is a choose-your-own-adventure, and we're only experiencing the ending where we make all the right choices.
So it's like reality is constantly editing itself, making sure we end up right where we're supposed to be.
Precisely. We're picking and choosing which outcomes we want to see, even if those outcomes, well, even if they defy our normal understanding of cause and effect.
Okay, my mind is officially blown. So, two totally wild models of quantum time travel. But here's the big question. Can we actually build a time machine? Could I, in theory, go back and finally get those winning lottery numbers?
Well, that's where things get a little more complicated. Even with all these amazing quantum theories, building a time machine for, well, macroscopic objects like people, it's incredibly unlikely.
Oh, come on. Why not? I'd love to have a chat with my past self. Maybe give her some helpful advice.
Well, the problem is, you see, quantum states are incredibly delicate. Entangling even a few particles is hard enough. But imagine trying to entangle all the atoms that make up a human being across different points in time. It's a task of almost unimaginable complexity.
Okay, so a full-blown hop-and-go time machine is still firmly in the realm of science fiction. I get it. But you're saying there's still hope for some kind of quantum time travel, right?
There is a tantalizing possibility, and it ties back into something we mentioned earlier. Remember retrocausality?
Yeah, those spooky particles talking to each other through time.
Exactly. Future physicists might be able to use retrocausality, to subtly influence quantum measurements in the past. Not changing big events, but sending tiny nudges, messages that ripple through time.
So instead of a time machine, we might be sending little quantum whispers to the past. That's pretty amazing. It's like instead of changing the past, we're nudging it in a different direction, like a cosmic butterfly effect. But what kind of messages are we talking about? Can I send my past self the winning lottery numbers? Or maybe some really helpful fashion tips?
Well, it's more about subtle influences at the quantum level, not specific instructions or predictions. Think of it this way. You're trying to influence the outcome of a coin toss.
Okay, coin toss. Got it.
You can't force it to land on heads every time, but you might be able to slightly nudge the probability.
So no lottery numbers or fashion advice, I get it. But still, it's a pretty wild concept. But why should we even care about all of this? Is this just theoretical fun for physicists, or are there actual, real-world implications for us non-time travelers?
That's a great question. And the answer is the study of quantum time travel has some incredibly exciting practical applications. It could completely revolutionize the field of metrology, which is all about making really, really precise measurements.
So time travel could help us measure things better. That's pretty cool, but what else? I'm all about practical applications.
Think about quantum computing and game theory.
Quantum computing, now we're talking.
Imagine a quantum computer that can actually prevent cheating by making decisions dependent on actions taken in the future, or a game where your strategy is shaped by knowing things that haven't even happened yet.
Okay, my mind is officially blown.
It's mind-boggling stuff.
This is seriously one of the most mind-bending deep dives we've ever done. Bendy space-time, spooky particles, time travel paradoxes, messages through time. I think I need a break to process all of this.
It is a lot to take in.
But we've only just scratched the surface of this mind-boggling topic. And thinking about, sending messages through time, it makes you wonder, like, those flashes of inspiration we get, those sudden bursts of creativity, could those actually be, like, subtle nudges from our future selves, guiding us towards something amazing?
Now, that's a thought-provoking idea. But let's bring it back down to Earth for a moment. Let's dig a bit deeper into the science. We've been talking about these theoretical models, but did any of the sources actually explain how this quantum time travel might work in practice, I mean?
You know what? I was just thinking the same thing. We've got all these crazy concepts, but how do we go from, like, theory to reality? Luckily, one of those academic papers we dug up, Quantum Mechanics of Time Travel Through Post-Selected Teleportation, actually gets into the nitty-gritty details.
Ah, yes. That paper, it really gets into the weeds, doesn't it? It talks about creating something called a post-selected closed timelike curve, a P-CTC. Sounds pretty complex, but the basic idea is surprisingly similar to something you might be familiar with: teleportation.
Wait, teleportation? Like beaming someone up? Star Trek style. Sign me up.
Haha, not quite that dramatic, but the core idea is similar. Remember those entangled particles we talked about?
Yeah, spooky action at a distance.
Exactly. Quantum teleportation uses entanglement to transfer information about a particle from one place to another. It's like sending a blueprint so you can recreate the particle somewhere else.
Okay, I'm following. But how does this connect to time travel? We're just moving particles around, right? Not sending them through time.
That's where the P-CTC comes in. The paper proposes combining teleportation with this post-selection process. So imagine two entangled particles, A and B.
Okay, A and B.
Particle A goes into the P-CTC, essentially traveling through time. Meanwhile, you make a measurement on particle B in the present. But here's the twist. You only pay attention to the outcomes where particle A comes back from its time-traveling journey in a state that matches your measurement on B.
So we're basically picking and choosing which outcomes we want to see, even if those outcomes, like, defy our normal understanding of cause and effect.
Precisely. And because this whole process depends on quantum measurements, which are inherently unpredictable.
Right, that whole randomness thing.
It brings chance and probability into play.
Okay, I think I'm starting to get it. We're setting up these entangled particles to, like, meet up in the past based on how we observe them in the present. It's like we're playing time-traveling matchmaker.
Haha, I love that analogy. And this opens up some really strange scenarios. The paper even describes how a particle could essentially teleport itself back in time.
Wait, a particle entangling with its future self? How is that even possible? It's like shaking hands with yourself from the future.
Remember, in the quantum world, particles exist in this hazy state of possibility until we measure them. So this particle, it's in a superposition of being in both the present and the past. And through entanglement and post-selection, we can make it interact with its past self.
Okay, that's seriously trippy. But if we can actually do this, create these P-CTCs, wouldn't that mean we could change the past?
That's a big question. And it really gets to the core of what's actually possible with this kind of time travel. The paper emphasizes that even with P-CTCs, you can't change events that have already been measured.
So no going back to prevent that awkward moment in middle school.
Afraid not. Think of it this way. You can't go back and change the fact that you had cereal for breakfast this morning.
Good, because that was a delicious bowl of cereal.
Exactly. That event has already been observed. It's set in stone. But events that haven't been measured yet, those might still be up for grabs. At least at the quantum level.
Okay, so no changing the past, but maybe subtly influencing events that haven't happened yet. More like nudging the outcome of a coin toss than, rewriting history.
Exactly. And even those subtle nudges could have huge consequences. Imagine being able to slightly influence a quantum measurement in the past, and that sets off a chain of events that leads to, say, a groundbreaking scientific discovery or a technological breakthrough.
So it's less about changing the past and more about shaping the probabilities of the future. It's like a quantum butterfly effect then.
Precisely. And what's even more fascinating is that this whole subtle influence idea, it might not just be limited to a lab. Remember that New Scientist article we mentioned? Well, it proposes a thought experiment where physicists from the future use retrocausality to actually send messages back to the present. Messages encoded in the states of entangled particles.
Wait, hold up. Messages from the future. Like stock tips, lottery numbers, spoilers for the next season of our favorite show.
Not quite that advanced. It's more about subtle hints, bits of information. Think of it like sending a telegram through time, but instead of words, we're sending quantum states. which can then be decoded to reveal information.
Okay, so maybe not louder numbers, but still pretty cool.
Yes.
It would be incredible to prove that time travel, even at the quantum level, is real. But if future physicists could send us these messages, what's stopping them from being more specific? Why not send us the cure for cancer? Or the solution to climate change?
Remember, we're dealing with the inherent randomness of quantum mechanics. It's like trying to send a really detailed message using a series of coin flips. You can convey some information, but the level of detail is limited by, well, by that randomness.
Got it. Quantum whispers, not full-blown conversations. But this brings up another question. What does all of this tell us about time itself? Is it really like a river flowing from past to future? Or is it something else entirely?
That is a profound question, and that YouTube video we have featuring the work of David Deutsch, well, it tackles that question head on.
Oh yeah, Deutsch, the Deutschian CTCs guy. What does he have to say about the nature of time?
Deutsch argues that our everyday experience of time as this flowing present is actually an illusion. He suggests that the laws of physics, they don't distinguish between past, present, and future. They just describe relationships between events without any inherent direction.
Wait, so you're saying that time, as we experience it, might not even be real, that our perception of past, present, future is just a construct? That's mind-blowing.
It's definitely a radical concept, but one that makes more sense when you consider quantum mechanics and, of course, the possibility of time travel. Deutsch proposes that reality is actually a massive collection of moments, each representing the entire universe at a specific point in time. But these moments don't flow, they simply exist, like a giant cosmic photo album.
So instead of a river, time is more like a giant photo album.
Yeah.
With each photo capturing a snapshot of the entire universe. That's a really interesting way to think about it. But how does this timeless reality affect cause and effect? If everything is just a collection of moments, how can one event cause another?
Excellent question. And it really gets to the heart of how our understanding of time influences our understanding of causality. You see, in a timeless reality, the idea of one event causing another, it becomes a bit more nuanced. It's not about a linear sequence of events, but rather it's about relationships between these events within the grand tapestry of, well, of existence.
So instead of A causing B, it's more like A and B are connected in this web of relationships outside of our linear perception of time. That's a huge shift in perspective.
Absolutely. It challenges our deeply ingrained intuitions about how the world works. Maybe, just maybe, our human brains perceive time as linear simply because it's easier to process, but the true nature of time might be far more complex, far more interconnected than we can currently grasp.
Wow, this is deep, deep stuff. But it's also incredibly exciting. It makes you wonder what other limits, what other assumptions about time might be holding us back from truly understanding the universe.
Exactly, and that's what makes these explorations so compelling. We're challenging those fundamental assumptions about reality, pushing the boundaries of what we thought was possible. It's a journey that's constantly evolving, constantly unfolding.
Well, before we get too lost in the philosophical weeds here, maybe we should pause, take a breather, and recap what we've covered so far. We've been through quite a whirlwind of information. Entangled particles, post-selected teleportation, messages from the future, a timeless reality. What are some key takeaways for our listeners to ponder?
I think the first takeaway is that the laws of physics, as we currently know them, don't rule out time travel. They might even provide a framework for it, especially when you consider the world of quantum mechanics.
Right. We talked about those closed time-like curves, the CTCs, which are essentially loops in spacetime. They could, in theory, allow for actual journeys into the past. And that idea comes straight from Einstein's theory of general relativity.
Exactly. But then we have quantum mechanics, which introduces entanglement and retrocausality. Those concepts could maybe, potentially, help us resolve those pesky time travel paradoxes.
Like the classic grandfather paradox, right? Where you go back and accidentally prevent yourself from ever being born. But it sounds like quantum mechanics might have a few tricks up its sleeve to help us avoid those sticky situations.
Exactly. And that leads to the second key takeaway. Even if time travel is possible, it might not be anything like what we see in movies. It's probably not about hopping into a DeLorean and zoom off to the past. We're talking about subtle influence, manipulating probabilities on the quantum level, and perhaps even sending those quantum whispers through time using entangled particles.
Right, shaping the future, not changing the past. And as we've discussed, it might require us to completely rethink how we see time itself. Remember David Deutsch? His idea that time, as we experience it, might just be an illusion, and reality might actually be a collection of static moments.
That's a question that really gets to the heart of it all, doesn't it? And it might be a question we never fully answer. But it speaks to how profound these explorations really are. It forces us to question our assumptions, to really examine our understanding of reality, consciousness, even existence itself.
Well, on that mind-bending note, I think it's time to shift gears a bit
Yeah.
and explore another layer of this quantum time travel conundrum, ready to go a little deeper down the rabbit hole.
Always. The deeper we go, the more intriguing the mysteries become.
Okay, so we've been focusing on how quantum time travel might allow us to influence the past, right? But one of our sources, a paper titled, get this, Replicating the Benefits of Deutschian Closed Timelike Curves Without Breaking Causality, takes a totally different approach. They're proposing a way to harness the computational power of time travel, but without actually messing with causality.
Ah, yes, that paper. It's a fascinating exploration of quantum mechanics, computation, and of course time travel. And it suggests that maybe, just maybe, we can get all the cool benefits of closed time-like curves without having to worry about those pesky paradoxes that, keep us up at night.
Okay, now you've got my attention. How can you have the benefits of time travel without the risk of erasing yourself from existence? It's like having your cake and eating it too.
It is a bit like having a virtual slice of cake. The paper argues that we can create a system that behaves as if it has access to a closed time-like curve, even though it doesn't actually send anything back in time.
So like a time travel simulator.
You could say that. The key is to create a quantum system that can essentially sample information from its future self without actually sending any information back in time.
Okay, that sounds like some serious quantum magic. How does that even work?
It involves entanglement, of course, and a process called open time-like curves, OTCs. So imagine a particle that enters an OTC. Instead of looping back in time, it emerges from the OTC at a later point in time. But crucially, it hasn't interacted with its past self. It's like taking a shortcut through time without altering anything along the way.
So it's like fast-forwarding a video, but without changing the content.
Exactly. Now imagine you entangle this particle with another particle that stays in the normal flow of time. The particle that went through the OTC, it's carrying information about its future state, which we can access by measuring its entangled partner right now in the present.
So we're sending a scout ahead in time.
Yeah.
Gathering intel without interfering.
A fantastic analogy, and that intel, that information about the future, it could be incredibly valuable. The paper shows how this technique could be used to enhance quantum measurements or even solve really complex problems way faster than classical computers.
Hold on, time travel simulators could boost our computing power. That's wild. What kind of problems are we talking about here?
The paper specifically focuses on what are called NP-complete problems. They're a class of, they're incredibly difficult computational challenges. Even the most powerful computers we have now struggle with them. These problems, they often involve finding the best solution out of a huge number of possibilities, and they have real-world applications too in fields like cryptography, logistics, even artificial intelligence.
So we could crack unbreakable codes, optimize global supply chains, develop truly intelligent AI, all thanks to virtual time travel.
The possibilities are tantalizing, to say the least. And the best part, it sidesteps that whole causality problem. We're not changing the past. We're just using quantum mechanics to get a peek into the future.
Okay, my brain is doing somersaults right now. But this is seriously cool stuff. It's incredible to think that we might be able to use time travel, even in a simulated form, to solve some of the biggest problems we're facing.
It's a testament to the power of quantum information science. We're still just scratching the surface, and who knows what other mind-blowing applications are out there just waiting to be discovered as we keep delving deeper into the quantum realm.
This is definitely a deep dive I'm going to have to revisit to fully wrap my head around it all.
I think more than anything, it's crucial to remember that our understanding of time, it's far from complete. The very idea of time travel, once pure science fiction, is now a serious topic of scientific inquiry. And it's making us question everything we thought we knew about reality and the limits of what's possible.
And who knows, maybe someday those limits will vanish entirely, opening up possibilities we can't even begin to imagine. Okay, so we've covered a lot of ground here. The theoretical side of time travel, quantum mechanics, even those virtual time travel simulators. But there's one question I think everyone is wondering. If time travel is actually possible, has anyone, actually done it? Have we had any visitors from the future?
That's the big one, isn't it? The quest for, well, for proof of time travel. It's something people have been thinking about for centuries. But as far as we know, no one's built a working time machine and, gone gallivanting through time.
Okay, but what about those experiments we discussed, the ones using post-selection and teleportation? They were like manipulating time in a pretty serious way. Couldn't those be considered a form of, I don't know, time travel?
Well, they do involve messing with time at a quantum level, that's true. But it's important to remember those experiments, they're working with single particles or tiny groups of particles. Scaling that up to, macroscopic objects like people, well, that's a whole different ballgame.
Right, like entangling every atom in a person across different points in time? Yeah, that sounds pretty impossible. But what about evidence of time travel from, I don't know, other places? Did any of the research we looked at offer any hints, clues?
Yes. One of our sources does touch on this. The encyclopedia entry on closed time-like curves. It mentions a specific solution to Einstein's equations, discovered back in 1949 by Kurt Gödel. And this solution, it describes a universe where time travel isn't just possible, it's a built-in feature.
Hold up, a universe where time travel is just like a regular Tuesday? Are we talking parallel universes, alternate dimensions?
Gödel's solution, it describes a rotating universe where these closed time-like curves, those time travel loops, they're everywhere. Time travel wouldn't be a weird thing. It would just be, normal.
That's crazy. So are we living in one of those Gödel universes? Is that why we haven't met any time travelers? Maybe they're all from a different reality where time travel is like hopping on the subway.
Haha. It's a fun thought. But the evidence we have suggests that our universe, doesn't really fit the description of a Gödel universe. Things like the expansion of the universe and the cosmic microwave background radiation, they point to the Big Bang, not a rotating universe.
Okay, so no time travelers popping in for a visit from other realities. That's kind of a bummer. But it's still amazing to think that there's a solution to Einstein's equations that describes a universe where time travel is just a fact of life. It really makes you wonder what else is out there.
Absolutely. And it reminds us that our understanding of the universe, even with all the advances we've made, is still limited. We're always learning, always finding new things, always pushing the boundaries of what we know.
So the question of whether time travel is possible, whether it's happening somewhere out there in the vastness of space, it's still open then.
For now, yes. But even asking these questions, grappling with these mind-bending ideas, it shows the power of human curiosity, our drive to understand the universe we live in.
That's true. And on that note, I think it's time to wrap up this deep dive. We've explored the mind-blowing possibilities of quantum time travel, the theories, the experiments, even the philosophical implications of a universe where past, present, and future are all connected. It's been quite a journey.
It has. And while we may not have all the answers, I think we've gained a new appreciation for the incredible mysteries that are still out there.
Absolutely. Who knows what incredible discoveries await us as we keep exploring, keep pushing the limits of what we know. Maybe one day the impossible will become possible, and the secrets of time travel will be revealed not in science fiction but in the textbooks of the future.
Until then, the adventure of discovery continues.
And as always, dear listeners, we encourage you to keep exploring, keep questioning, and keep your minds open to the infinite possibilities that are out there.
Because the universe is a place of wonder and the pursuit of knowledge. That's the greatest adventure of all.
This has been The Deep Dive, and we'll be back soon to embark on another thrilling expedition. Until then, stay curious, keep those imaginations firing, and we'll see you next time.